All right, everyone, this is Zahid Bashir, and you are here with me for Stata training for day 8. And today we are going to discuss the remaining commands that we have discussed in our previous session. Yesterday, we have discussed the multicollinearity in greater detail, and today we will cover the next part that is basically residual normality. That is the fifth assumption because the fourth one was multicollinearity. So we have discussed in greater detail the multicollinearity. So today we are going to discuss the assumption number 5, that residue should be normally distributed. Now, there is a difference between normality of your data and normality of residues. Always remember that when someone is asking about the normality, always try to ask whether he or she is asking about the normality of the data or normality of the residuals, because there is a difference between both terms. When we are asking about the normality of the data, it's mean normality on the basis of your sample size. And when someone is asking about the normality of the residue, it does not depend upon your sample size. So you need to understand both terms: normality of the data, normality data, and residues. Normality of the data is basically relative to sample size. According to sample size theorem, or you can say the bell-shaped curve or symmetric distribution theorem, we have at least 30 observations to declare the normality of our data. So if our data set has at least 30 observation, or at least our sample size having the 30 observation, our data would be considered as normal. But if our data has less than 30 observation, then we need to check the normality of our data. This is the thing that you need to understand. So if someone says that he basically required to check the normality of your data, he is basically discussing about the sample size. So if your sample size is less than 30 observation, then you need then you need normality of your data, whether it is normal or not. But if your sample size is at least 30 observation or more, then it is considered by default that it is a normal distribution. Now, what is normality of residues? What does it mean? Residues are the error terms. When we create a model, the error term basically needs to be normally distributed. If you create a model, for example, y is equal to alpha plus beta into x1 and so on, plus error term. So this is particular error term, you would say it as a residual. It should be normally distributed according to the assumption. So here the assumptions mean the normality of your error. So it does not require whether your sample size is 30, less than 30 or more than 30. Whenever your sample size is more than 30, you still need to check the normality of your residuals. So it does not matter. It does not matter whether your sample size is less than 30 or more than 30. You still needs to check the normality of the residuals. But there is a difference between normality of data and normality of residue. So what we are considering here, we are considering assumption 5 as a normality of the residues. So you need to check that residual or error of the regression lines are approximately normally distributed. Technically, normality is necessary only for hypothesis test to be valid. It means if your residuals are not normal, your hypothesis may not be valid. So, estimation of the coefficient only requires that error be identically and independently distributed. So, two common methods to check this assumption includes using either a histogram with superimposed normal curve or a normal PP plot. This is basically the graphical criteria of testing the normality of residuals. So how can we check uh, normality using this method? You need to run a regression. You need to predict your error term or your residual term. Then you need to create k density plot of your residual term in order to check the normality. Then you need to create a histogram of your residual with k density normal. Then you can check p normal and q normal. In some other session I have used this procedure, but today I am going to repeat it again for your convenience. So let's have a quick recap of this procedure for your understanding. Adnan Afzal is asking residual error term are control variables. No, this is not control variable. It is a part of our model. If you see any econometrics model, let me show you some models here. Let me open the file first. I would like to show you some model like, for example, this paper. If you see any paper, you would find an econometric model. Like I will show you this one. You can see here an econometrics model like delta YIT alpha, then delta YIT1, and this is error term. Error term basically indicates those factors which you have not included in your model. It may contain some variables that you may have not included in your model. So what we are doing, we are checking the normality of this residual term in your regression model. So in this case, this is the procedure. This is the graphical procedure. If you need to check the normality of your residuals in a graphical way, this is the graphical procedure. So let me open the same data set that we are using previously, which is CG data or corporate governance data. I have shared that data with you. So I am using it again for this analysis. So here, what is the procedure as per this graphical method? First, you need to run the regression. So let's suppose I am going to run a regression by writing reg, then my DV, that is Tobin's Q. Then one by one, I put my IVs, IV1, IV2, IV3, IV4, IV5, IV6, IV7, IV8. Let's suppose these are my variables. The Tobin's Q is dV, and these are IVs. So first, I need to run the regression as a part of this process for checking the normality of the residue. So after running the regression, next what I need to do, I need to predict my residual using this command. So just copy this command from here and paste the command here, predict E residue. Click enter, and you will see on the right side that E is created, which is not previously there. You can also verify the data of E from the data editor. You can open it. You can open the data editor and you will see values of E like this. So this is created. This is you have created the values of E or values of your error term. So these are created with the command that I have tell you. So here predict E residue. You have created the E. Now what is the next? You need to create key density E normal. This command is for creating key density or kernel density plot for checking the normality of your data. So you need to put this command here and click enter, and you will see a graphical distribution of your normality of residue. So it is processing. You can see here it takes some time and it will show you whenever this circle is complete. So you can see here the kernel density estimates. The red curve is basically the estimated curve, which shows the normality of the data, while the blue curve is basically the estimated values of your residuals. So blue curve is very away from your red curve. It means there is a issue of normality according to kernel density estimate. But we need to we cannot finalize normality on the basis of just on this single measure. We need to check other measures too. Like there are a lot of measure like histogram E density normal. You can also use this command here. You just need to paste this command here, and you will find a picture like this. Now this is histogram based picture. It is showing that the actual data is showing the highest peakedness rather than the central data. So again, it is showing that there might be some issue of normality in this data set. So we can further interrogate the issue of normality in our data by further commands. Like there is a p normal command here. You just need to copy this command and you need to paste this command here, and you will find it requires a var list. All right, p normal, and you need to put a var list here like this. Just need to put here var list and click enter. Too many variables specified. Let's suppose I am going to check p normal with Tobin's Q only. So what will happen? Is it able to run it? Let me see. It is working. It is basically processing. So you can hear, you can see uh, that this is the predicted line. The central line is predicted line, while the actual one is deviates from the center, somewhat deviates from the center. So you can say that there might be some issue with the normality of the data, but we are still unable to confirm. We can also use q normal command. Let me use it. Normal. It also required the var list. It means with q normal, I should use the dependent variable. The dependent variable is Tobin's q. Click enter, and we will see q normal. It also showing some deviation from the center. So how can we confirm whether our residues are normal or not? We need to go to the non-graphical procedure. The non-graphical procedure will let us confirm whether our residues are normal or not. So there are several normality tests such as Kunis-Kurtosis test, Jerk-Barra test, and Shapiro-Wilk or SW test, Kolmogorov-Smirnov test, and Chen-Shapiro test. So there are a lot of tests that we can apply in order to check the normality of our data. Always remember that in order to run uh, all these tests, you need to have your residuals. If you have already created your residue, like using this command, then these tests may apply. If you have not created your residual, like I have shown you in our data set, these are the residuals values. So if these are created, then the non-graphical procedure will work. Otherwise the non-graphical procedure will not work. So in order to apply this, as we have already created the e or residues, so we can run this procedure. First is to run the regression. So we will run the regression again every time you apply a fresh procedure. You need to run the regression again. So we run the regression first. Then what is the procedure? That is sk test e. So we need to paste here the actual command and then press enter, and it will run this Hughes kurtosis test. Here you need to see the p-value or pr value. If these values are significant or these values are less than 5%, it means your data, your residues are not normal. Always remember that these PR values should be greater than 5% in order to make your residuals normal. Here I have interpreted. If p value is less than 5%, your residuals are not normal. It means assumption is violated. If your p value is greater than 5%, your residuals are normal. So our p value is less than 5% here. You can see these are less than 5%. Even they are less than 1% too. So we can conclude here that our residuals are not normal and our assumption is violated according to this criteria. That is why the graphical procedure is also showing the same one. The graphical procedure was showing that data was not normal. So our assumption number 5 is violated because our data is not normal. We can also verify uh, through the other test too. We can run will e test. It is also another test for checking the normality of your residuals. So here, this is the p value. You can see again it is less than 5% and even it is less than 1%. So again, our the normality of our residual is still compromised. So we can again interpret it that residual are not normal. uh, Another test, which is Jerk-Barra test for normality, it is also very renowned or popular test for checking the normality. So again, you can write JBE here and you can check the normality. The command JB is unrecognized because this is the command that recently introduced in Stata. So you need to install this command every time when something is unrecognized in Stata. You need to install that one. So the installation procedure is SSC install. The one which is not installed here is JB. Press enter and it will process the command. It is checking JB consistency and verify not and already installed, and the installation is complete. It has automatically installed this command. Now you can use this command JBE. Now if you run this command, you will see the value 0. It is basically indicating the p value as 0. This value should also be greater than 5%, but it is less than 5%. Therefore we can interpret here that our data is not normal. So what to do now? It is confirmed that our data is not normal. What to do now? If residue do not follow a normal pattern, when you should check for omitted variables, model specification, linearity, functional forms. uh, Always remember, when it is confirmed that your data is not normal, you need to check four things. you need to check the variable omission. If your data or if your residues are not normal, but further things you need to check. Then you need to check, first thing is whether some variable is omitted from the model, which is known as variable omission. Model specification and linearity. These are the further consideration that you need to confirm. So how can we confirm whether these are violated or not? If residual are not normal. So I have highlighted these procedure. uh, I will let you know how the variable omission is basically checked. First of all, I will like to clear you about the variable omission. So this is the first consideration that you need to check after it is confirmed that your residues are not normal. So how do we know we have included all variable? We need to explain why. Why means dependent variables. We omission means that we might have omitted some important variable from our model, and we may have included some irrelevant variable in our model. You have already observed in the regression result that there are some variables which are not significant our model. You can observe here, and you also observe here that r square is very low. It is only 20%. It should be close to 1. It should be more than 50%, but it is very low. It means there is a chance that we may have skipped some important variable in our model. So how can we confirm that? There is a command of testing the omitted variables. So testing for omitted variable bias is important for our model, since it is related to assumptions that the error term and the independent variable in the model are not correlated. You may have listened about endogeneity test. Endogeneity is a condition where independent variable in the model may have correlated with error term. So sometimes when we skip or we omit some important independent variable, they may correlate, the omitted variable may correlate with the error term. That may create endogeneity issue. So if we are missing variable in our model and it is correlated with the included regressor, the omitted variable is determinant of the dependent variable, then our regression coefficient becomes inconsistent. In Stata, we test for omitted variable bias using the OV test. So this is the command which we basically use for testing the variable omission. So first we need to run the regression with robust test. So let's copy this regression and include comma ROB, which is the robust. Click enter. The procedure has run. Now we need to check the OV test. OV test, that is variable omission test. OV test. So it will let us know, it gives us a value which is less than 5%. So what is the interpretation of this value? We need to see the interpretation. If p value is less than 5%, variable is omitted. We need to add more variable to explain why. So our first consideration is basically confirmed. Why your residuals are not normal? Because variable omitted. So this one was confirmed here. So you can confirm here that your variable is omitted. Now you need to confirm your second consideration, that is model specification. So how you can confirm whether your model is correctly specified or not? Another command to test model specification is link test. What does we mean by model specification? Sometimes uh, the model that we are testing is not a good model for our estimation. So we need to confirm whether the estimation technique we are going to apply is good for our model or not, or we need to change the specification. So another command which is used to test the model specification is link test. This is basically the command which we are going to test for our specification error. It checks whether we need more variable in our model by running a new regression with the observed y against y hat. It will also confirm that, as we have confirmed that we need more variable in our model. So we need to confirm that if we include more variable in our model, so whether the model would be good for us or not. So it will confirm, it will verify your first assumption too, because in case of variable omission we need to add more variables. So model specification will confirm that by adding more variable, is it good for our model or not. So the thing to look for here is the significance of hat square. This is the thing that we need to check for. The null hypothesis is that there is no specification error. If p-value of hat square is not significant, then we fail to reject the null hypothesis, and that our model is correctly specified. So if p-value is less than 5%, specification error exists. Our model is misspecified. But if p-value is greater than 5%, no specification error exists. Our model is correctly specified. So we need to check this one. So how can we check? We need to run the regression, and then we need to run the link test. So first of all, we need to run the regression again, like this one. Then we need to write link test, link test. And here you need to see the value hat score here, hat square. Basically, we need to see this value, because according to the criteria, the thing to look for here is the significance of hat square. So if the hat square value indicates a value less than 5%, it means specification error exists. So if you see here, the value of hat square, its p value is less than 5%. So it means there is a specification error. So it means we need to we need to consider adding, because specification error is. All right. Third thing is linearity. We have confirmed the linearity from here. If something is significant, it means it is linear. So we have a lot of variables which are linear in our model, and we have previously checked this condition as a first condition in our assumption testing. The first condition, if you see uh, in our file that I have previously shared with you, like this one, the first condition was linearity. I would like to show you here. Yes, this one. The first assumption was linearity, and we have checked the linearity, whether our model is linear or not. So some of the variables shows linearity, and some of the variables does not show linearity. So it was obvious that we need to transform our data. So if these conditions are violated, what we need to do? So for example, it is confirmed that variables are omitted. So we need to add some variable. And it is also confirmed that we need to consider model specification. So if your data is not normal and OV tests have p-value greater than 5%, then you need to increase the number of observation in your data. But in our case, uh, uh, the residues were not normal, and PV test also indicates significant. So what we need to confirm that we need to add variables in our model. We need to increase the variable of our model. So how it is justified? You can see here the regression. The R square value is too low. So adding some independent variable will definitely increase the R square. So those variables should be relevant. You need to study the literature. You need to find out what other variables still can impact your dependent variable. So you need to include those variables. You need to collect more data related to those variable in order to control this issue of variable omission until variable omission shows a value greater than 5%. In the same way, when the variable omission issue is resolved, the model specification issue will also be resolved. So this is how you can remedize these issues. So here, the following are the general guidelines for building a regression model. But before discussing it, I would like to discuss the remaining things here. I have discussed the normality. The next one is the assumption number 6, which is relevant to absence of autocorrelation or serial correlation. Autocorrelation or serious correlation or serial correlation is an issue with time series data. So whenever you need to use the time series data, then you basically need to consider the autocorrelation or serial correlation first. So this assumptions requires that errors are normally distributed with zero mean and constant variance. Errors are independent. Independence means one error term is not correlated to any other error term. So when in different observations in your data, the error term may influence the error term of the other observation. So it means both error terms are correlated. So when both error terms are correlated or error terms of different observation of your data are correlated with each other, this condition is known as autocorrelation or serial correlation. So violation of the above is called serial correlation. So but with cursor autocorrelation is only for time series data. In panel, we check it or not. Always remember that if you have a number of observation, because in panel you have time series dimension as well as you have cross sectional dimension. So you need to check the autocorrelation in panel 2. Uh, in case of pool data, you don't need to check this assumption. In case of time series data and in case of panel data, in both cases, there is a time dimension in your data. So you need to check this condition with the panel data too. So this assumption should not be violated in case of panel data too. So, but with serial correlation, error terms are correlated with one another. Error terms of different period, usually adjacent or different cross-sectional observation are correlated. If we know something about the error term of one observation, we know something about the error term of another observation. Technically, this means a lot. So error associated in one time period carry over a future period. Example of lag model. If you hear about the lag model, they are basically prepared to control for the serial correlation. So serial correlation is usually associated with time series data. So we will use a subscript T instead of I. Error term may be correlated with more nearby observation as compared to distance observation. So always remember that normally the error term are correlated with near observation. They are not correlated with distinct observations. So the error associated with one observation are not correlated with the error of any other observation. You should have independence of observation, which you can easily check using the Durbin-Watson statistic, which is a simple test in running using Stata. So how can you confirm that there is an issue of serial correlation in your data? You can use Durbin-Watson statistic. This is a test which is used for testing the uh, serial correlation in a time series data, as well as it can also used for panel data also. So this assumption state that the error associated with one observation are not correlated with error of any other observation covering several different situations. For checking this assumption, the data set need to be time series. Basically in panel, the time series is there. So you can also check this assumption with the panel data. So this assumption cannot be tested on pool data. Basically, this is the this statement requires some editing, so I will edit the revised version. You can check the this assumption with the panel 2. You cannot check this assumption with the cross sectional and pool data. So there is less than 1 minute for ending this meeting, but I will let you know that you need to join again with the same link, because the meeting is continued and it will be up to 5:45 to cover today's session. Both of you, Adnan Afzal and Vakar, please join the meeting again using the same link so that we can continue the session, because it is less than 1 minute, some seconds are remaining. So please join again.